The 13th of October 1943, Kagoshima Naval Air Station, southern Japan. Chief Engineer Takashi Miyazaki of the Imperial Japanese Navy stood on the tarmac, staring at the twisted wreckage that would soon challenge everything he thought he knew about aircraft design. The son of a shipbuilder who had served in the Japanese Navy during the Russo-Japanese War, Miyazaki had joined the Naval Engineering Corps in 1936. Now, as morning fog lifted over the airfield, he would witness something that contradicted every assumption about American technological capabilities. What he discovered in the next several weeks would shake the foundations of Japanese aircraft design for generations to come. The American planes were supposed to be inferior. On paper, they were. The Japanese had more agile fighters, more experienced pilots, comparable range. The A6M0 alone outperformed anything the Americans had put in the sky during the first year of the war and was regarded as the most formidable fighter in the Pacific. Japanese naval aviation had arrived with hundreds of combat-proven pilots, well-trained, confident in their equipment's superiority. Yet within months, the tide had turned. American Corsairs were dominating the skies. Japanese pilots were retreating. The mathematical impossibility had occurred. A supposedly inferior force had developed an aircraft that defied every Japanese analysis. This is not a story about numerical superiority. This is not a story about overwhelming resources alone. This is the story of how American engineers revolutionized fighter design through innovation, materials science, and manufacturing techniques so radically different from their enemies that they created performance that should have been impossible. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The transformation began not on the battlefields of the Pacific, but in the design rooms of Chance Vought Aircraft in Connecticut. February 1938. America watched war clouds gathering over Europe and Asia. The Navy had issued a requirement for a new carrier-based fighter that could outperform anything currently flying. Most aviation experts considered the specifications impossible. The fighter needed to carry an enormous 2,000 horsepower engine, 6 heavy machine guns, substantial armor protection, and still achieve speeds over 400 miles per hour while maintaining carrier landing capability. These requirements seemed mutually exclusive. More power meant more weight. More weight meant reduced maneuverability. Greater speed required larger wings, but carrier operations demanded compact dimensions. Most aircraft manufacturers proposed conventional designs with modest improvements. Rex Beisel, Chance Vaught's chief designer, made a decision that would reshape aviation history. If conventional approaches couldn't meet these contradictory demands, they would reinvent fighter design from first principles. Beisel's vision was revolutionary. He chose to create an airframe built around the massive Pratt & Whitney R2800 double Wasp engine, the most powerful aircraft engine then available. This was not mere ambition. This was systematic engineering that challenged every assumption about fighter design. Every single component would be optimized not just for its current role, but for the integrated performance of the entire aircraft. This was not theoretical engineering conducted in isolation. This was intensive practical development that assumed American pilots would soon face the world's best fighters in combat. The philosophy had deep roots stretching back through American industrial history. The American engineering tradition emphasized something called systems integration, holistic design. The concept was revolutionary in its simplicity and radical in its implications. An aircraft wasn't merely a collection of parts that functioned independently, but an integrated system where each component affected every other. This stood in stark contrast to the design philosophies of most aircraft manufacturers, where engines, airframes, and armament were often developed separately and then combined. Systems integration required collaboration. It required engineers who understood not just their specialty, but how their work affected the entire aircraft. It required leaders at every level who understood not just aerodynamics, but materials, manufacturing, and combat requirements. The American training system was designed to create exactly these engineers. Between 1938 and 1943, even as war spread across the globe, American aviation companies conducted experimental development on an unprecedented scale. These were not simple modifications to existing designs. These were massive, systematic reimaginings of what a fighter aircraft could be, conducted across multiple engineering disciplines simultaneously. Engineers tested radical new wing designs, cooling systems, and structural approaches that aircraft manufacturers elsewhere were not yet exploring. They wargamed scenarios involving carrier operations, high-altitude combat, and ground attack missions. The exercises were brutally honest. Failures were analyzed without mercy. Successes were studied for replication. Every engineer who participated was expected to prepare detailed reports that would be circulated throughout the industry. They studied the lessons of early war combat with unflinching analysis. The maneuverability-focused Japanese designs that had dominated early Pacific air battles were not the future. That approach had worked initially but showed fundamental limitations. Speed was the future. Firepower was the future. The ability to dive faster and climb more powerfully than the enemy was the future. These conclusions were not philosophical musings. They became the foundation of systematic development. The engineering teams, though theoretically competitors, shared crucial data under government coordination. Selected engineers underwent intensive courses that covered far more than aeronautical design alone. They studied metallurgy, understanding that new aluminum alloys could create stronger, lighter structures. They studied manufacturing, recognizing that production techniques would determine how quickly aircraft reached the front lines. They studied combat reports, learning to understand pilot needs and enemy capabilities. They studied logistics, recognizing that maintenance requirements would determine effectiveness in the field. They studied carrier operations, understanding how naval requirements shaped fighter design in ways land-based aircraft engineers never considered. The curriculum was comprehensive because American companies understood that modern air warfare required more than aerodynamic skill. It required engineers who could think structurally, operationally, and tactically all at once. The training emphasized something that would become crucial in the coming air war: innovative thinking within a framework of practical constraints. American engineers were taught explicitly that it was better to make a good aircraft now than a perfect aircraft too late. In war, delays meant death. Opportunity was fleeting, appearing and vanishing in moments. An engineering team that waited for perfect solutions, who delayed production until every uncertainty was resolved, would watch the war end before their designs reached combat. This principle was drilled into every engineer through countless development cycles designed to create pressure, uncertainty, and adaptation. The Americans recognized that combat was fundamentally unpredictable. No design survived first contact with the enemy intact. Therefore, engineers needed to be comfortable operating on the edge of possibility, making decisions with incomplete information, adapting as battlefield reports arrived. This created a culture where engineering teams were expected to solve problems without waiting for perfect solutions, where test pilots were integrated into design teams, understanding not just their immediate feedback, but how their input contributed to larger development goals, where every engineer understood that in the chaos of wartime production, the team on the ground often had better insights than the theorists in distant offices. The philosophy extended to something called concurrent development, progressing multiple aspects simultaneously. American designers did not perfect engines before addressing airframes or finalize structures before considering armament. They developed everything in parallel, with constant communication between specialties. This was risky. American companies experienced failures and setbacks at rates far higher than more methodical approaches. But the advantage in development speed was overwhelming. While Japanese engineers waited for each phase to complete before beginning the next, following proper hierarchical procedures, American teams were making decisions in real time based on emerging combat data. The difference in tempo was measured in months, sometimes years. By 1943, when the F-4U Corsair reached combat units in the Solomon Islands, America had spent 5 years building the intellectual and industrial framework for a new kind of fighter aircraft. The physical tools had been developed alongside the thinking, not sequentially. The engine, airframe, armament, and production techniques had evolved together, creating systems integration in its purest form. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The architect of the Corsair's distinctive design was Rex Beisel, a mechanical engineer who had spent the 1,930 seconds obsessed with a simple idea that most aviation experts considered absurd. Fighter aircraft should not prioritize turning capability above all else, following dogfighting traditions from World War I. Fighters should emphasize power, speed, and diving performance, allowing pilots to control when and how engagements occurred. This was heresy to aircraft designers across the world, who remembered the agile fighters of World War I and the early Japanese Zeros that could outmaneuver anything in the sky. Those nimble fighters had dominated early Pacific combat, shooting down slower American aircraft with apparent ease. But Beisel had studied emerging combat reports with a different perspective. He had examined how the air war was evolving, noting that pilots who could choose when to engage and when to disengage held a tremendous advantage regardless of turning performance. He had synthesized these ideas with American industrial concepts of mass production and reliability. The result was something aviation journalists would eventually call the whistling death, a nickname given by Japanese troops who heard the Corsair's distinctive sound. The concept was to create an aircraft with unprecedented power-to-weight ratio through a unique airframe design. The massive 2,000 horsepower engine required a propeller over 13 feet in diameter, so large that conventional landing gear would make the aircraft too tall for carrier hangar decks. Beisel's solution was revolutionary, the distinctive inverted gull wing that became the Corsair's signature feature. This allowed shorter, stronger landing gear, while still providing ground clearance for the massive propeller. This was not a stylistic choice. This was engineering that turned constraint into innovation. The inverted gull wing created additional benefits that Beisel's team hadn't initially anticipated. It reduced drag where the wing met the fuselage. It improved the pilot's visibility. It enhanced stability in certain flight regimes. This was systems integration producing emergent benefits beyond the original design goals. By mid-1942, the pieces were in place. The Corsair had moved from drawing board to production line faster than any aircraft of comparable complexity in history. It had the most powerful engine in any fighter worldwide. It had 6 heavy machine guns capable of delivering devastating firepower. It had an airspeed approaching 450 miles per hour, faster than anything the Japanese had even on their drawing boards. The technological advantage was crucial and often overlooked. While Japanese fighters still relied on traditional materials and manufacturing, American engineers had incorporated new aluminum alloys, spot welding techniques, and precision hydraulics that allowed unprecedented performance. This single technological edge created a massive advantage in combat capability. Every American aircraft worker had access to advanced machine tools, standardized parts, and quality control methods that Japanese production could not match. When Corsairs began reaching frontline squadrons, pilots discovered aircraft that maintained consistent performance across the production run, something Japanese pilots with handcrafted aircraft couldn't count on. The Corsair had been designed from the beginning to operate from aircraft carriers in the harshest conditions of the Pacific. Unlike the Imperial Japanese Navy Air Service, which emphasized pilot skill over aircraft durability, the Americans designed for maintainability, reliability, and consistent performance, even with average piloting. The Pratt & Whitney R2800 engine, that distinctive power plant that gave the Corsair its edge, was essentially flying artillery. It could deliver horsepower that Japanese engines couldn't approach while maintaining reliability in tropical conditions that wreaked havoc on more delicate machinery. Corsair pilots trained to use this power advantage rather than attempting to outmaneuver more agile opponents. American pilots learned tactics that maximized the Corsair's advantages. Rather than engaging in traditional turning dogfights where Japanese fighters excelled, Corsair pilots used what they called boom and zoom, diving attacks from altitude, high-speed firing passes, and climbing away before the enemy could respond. The aircraft's design enabled these tactics that opponents found nearly impossible to counter. Takashi Miyazaki, examining the captured Corsair at Kagoshima, experienced this reality firsthand. As his engineering team dismantled the American fighter that had crash-landed on Iwo Jima, he discovered construction techniques and materials that the Japanese aviation industry simply couldn't replicate. Under his skilled direction, the reverse engineering team performed what his superiors later described as prodigious feats of analysis, documenting every component of the American fighter, despite facing inadequate tools and the frightening reality of what their findings meant for Japan's air defense. Japanese aircraft, despite having excellent maneuverability in many cases, could not match the speed, firepower, or diving capability of the Corsair. The Japanese HAMP fighter was superior in turning radius and climb rate at certain altitudes, but Japanese pilots found themselves increasingly unable to dictate the terms of engagement. They couldn't force American pilots into the turning battles where Japanese aircraft excelled. Japanese engineers found themselves inside the American decision-making loop, operating at a tempo American development cycles completely outmatched. By mid-1943, American forces were producing Corsairs at a rate Japanese aircraft production could not hope to equal. They had covered design to deployment cycles in months that Japanese naval aviation required years to match. The crashed Corsair at Kagoshima revealed secrets that Japanese engineers had never imagined. As Miyazaki's team meticulously disassembled the fighter, they discovered a level of industrial precision that seemed impossible. The aluminum skin was machined to tolerances Japanese factories couldn't achieve with existing equipment. The engine components showed evidence of mass production techniques that maintained quality standards Japanese craftsmen could only dream of. How do they make these so quickly yet so precisely? Asked Hiroshi Nakamura, Miyazaki's assistant, holding a perfectly formed hydraulic fitting. The question hung in the air as the engineering team exchanged troubled glances. They all recognized the implications. This wasn't just a better aircraft. This was evidence of an industrial capability gap that might prove impossible to close. What troubled Miyazaki most wasn't just the Corsair's superior performance. It was how the Americans had solved problems Japanese engineers considered fundamentally contradictory. The massive R-2800 engine should have created cooling problems that made sustained high-speed flight impossible. Yet the Corsair's innovative ducting system, which Miyazaki's team was now reverse engineering, managed airflow so efficiently that the engine could deliver full power without overheating. They've approached this from first principles, Miyazaki said quietly, examining the unique oil cooling system. This isn't an improvement on old ideas. This is something entirely new. The truth was becoming unavoidable. While Japanese aircraft designers had been perfecting maneuverability and range based on pre-war requirements, American engineers had completely reimagined what a fighter aircraft should be. They had prioritized speed, power, and structural strength, creating an aircraft that could dictate combat on its own terms. As Miyazaki's team completed their analysis, their report to Imperial Navy headquarters contained a conclusion that few wanted to hear. We cannot match this aircraft's performance with current design philosophies or manufacturing capabilities. The report documented a 70 miles per hour speed advantage, diving capabilities that no Japanese fighter could match, and firepower that outclassed anything in the Japanese arsenal. When Vice Admiral Jisaburo Ozawa reviewed the findings in February 1944, he summoned Miyazaki to naval headquarters in Tokyo. "Is there any way to close this capability gap quickly?" he asked, sliding the report across his desk. Miyazaki hesitated, weighing patriotism against professional integrity. "Not with existing resources, Admiral. The Americans aren't just building better aircraft, they're building them differently, using techniques we haven't mastered." This reality was difficult to accept for leaders who had witnessed the Zero dominate Pacific skies just 2 years earlier. The A6M0 had been revolutionary when introduced, lightweight, agile, with tremendous range. It had outclassed everything the Americans initially fielded, but the Zero's advantages came with compromises that seemed sensible in 1940 but proved catastrophic by 1943. To achieve its exceptional range and maneuverability, the Zero sacrificed pilot protection and structural durability. It lacked armor plating and self-sealing fuel tanks. Its light construction couldn't withstand the punishment American fighters could absorb. A single burst from a Corsair's 6.50 caliber machine guns could tear a Zero apart, while Zeros often landed dozens of hits on Corsairs without securing a kill. The philosophical difference was stark. Japanese naval aviation had designed aircraft around the skills of elite pilots with thousands of flight hours. American aviation designed for industrial production, maintainability, and the realities of training thousands of new pilots quickly. When elite Japanese pilots began falling in combat and being replaced by hastily trained novices, the paradigm collapsed. By mid-1944, as Miyazaki completed his analysis, the implications were becoming clear across the Japanese naval establishment. American aircraft production was reaching levels that seemed impossible, over 96,000 aircraft in 1944 alone, compared to Japan's 28,000. Quality wasn't being sacrificed for quantity either. American aircraft were becoming more sophisticated, more powerful, and more deadly with each production block. What Miyazaki couldn't fully document was how this production miracle had happened. What he didn't know was that the American aircraft industry had undergone a transformation as revolutionary as the aircraft it produced. Companies like Chance Vought had reimagined manufacturing from the ground up, implementing systems that would change industrial production forever. When the Corsair entered mass production, Chance Vought employed something revolutionary: statistical quality control. Unlike traditional manufacturing where skilled inspectors checked finished products, statistical methods monitored the production process itself, identifying problems before they affected final assembly. This system, pioneered by statistician W. Edwards Deming, allowed unprecedented consistency with less skilled labor. Women who had never worked in factories before, the famous Rosie the Riveters, were quickly trained to perform specialized tasks to exacting standards. The workforce expanded exponentially without sacrificing quality. By 1943, American factories were producing aircraft at rates Japanese leadership considered mathematically impossible. The Chance Vought plant in Connecticut operated around the clock, 3 shifts daily, 7 days a week. Raw materials entered one end of the facility, and complete Corsairs emerged from the other at a rate of 1 aircraft every 4 hours. This wasn't accomplished through superior resources alone. It came from systematic rethinking of how complex machines could be built. Assembly lines were reconfigured to optimize flow. Workers performed specialized tasks rather than building entire components. Engineering was standardized to facilitate interchangeable parts across production runs. These concepts seem obvious today, but they represented a revolution in aerospace manufacturing. What made this transformation possible was American industrial culture. Unlike Japanese manufacturing, which valued craftsman traditions and individual skill, American production embraced standardization and systemization. Engineers weren't just designing aircraft, they were designing the systems that would build those aircraft by the thousands. Lieutenant Commander James Sergeant Fletcher, flying with VF-17 Jolly Roger's squadron from Bougainville in late 1943, experienced the results of this industrial revolution firsthand. As he engaged a formation of Japanese fighters over Rabaul on November 11th, he witnessed the performance gap Miyazaki was documenting from the opposite perspective. Fletcher dove his Corsair from 22,000 feet, accelerating past 450 miles per hour, a speed Japanese fighters simply couldn't match. He selected a Zero at the formation's edge, closed to 300 yards, fired a 3-second burst from his 6.50 caliber machine guns, and pulled away, climbing at full power. The Zero erupted in flames and spiraled toward the ocean below. Fletcher was already thousands of feet above the remaining Japanese fighters before they could react. This wasn't just superior flying skill. It was the practical application of Beisel's design philosophy: create an aircraft that could dictate the terms of engagement. Fletcher could choose when to attack and when to disengage. Japanese pilots, regardless of skill, found themselves tactically disadvantaged by the performance differential. As Fletcher described in his after-action report, "The Japanese pilot never saw me coming. By the time his wingman reacted, I was already climbing away faster than they could follow. This wasn't a dogfight. It was a hit-and-run attack they had no answer for." These combat reports filtered back to Miyazaki through intelligence channels. They painted a picture consistent with his engineering analysis. American pilots weren't winning through superior numbers alone. They were employing tactics that exploited their aircraft's performance advantages with devastating effectiveness. The Corsair's capabilities were transforming how air combat functioned in the Pacific theater. Traditional dogfighting, the turning, twisting ballet of agility that had defined aerial combat since World War I, was being replaced by high-speed slashing attacks. Power, speed, and firepower were proving more important than turning radius. By March 1944, as Miyazaki completed his comprehensive analysis of the Corsair, Japanese naval aviation faced an impossible situation. Pilot losses had become unsustainable. Aircraft production couldn't keep pace with American output. The qualitative edge that Japanese designs had enjoyed early in the war had not just disappeared, it had reversed completely. Miyazaki's final report to the Naval Air Technical Arsenal contained recommendations that represented a complete philosophical shift. We must abandon our current approach to fighter design and embrace concepts that prioritize power, protection, and speed over maneuverability and range. This was heresy to traditional Japanese naval aviation doctrine, which had emphasized the dogfighting skills of elite pilots since the 1920 seconds. But the evidence was irrefutable. In a comparison test flight using the reconstructed Corsair against Japan's best operational fighter, the Corsair demonstrated a 78 miles per hour speed advantage, could climb to 20,000 feet 4 minutes faster, and could dive at speeds that would tear the Japanese aircraft's wings off. The Japanese response came too late. Projects like the Kawanishi N1K2 J Shidenkai George incorporated some of Miyazaki's recommendations: more powerful engines, better protection, heavier armament. But these aircraft entered production in early 1944, when material shortages, fuel constraints, and pilot losses were already crippling Japanese naval aviation. The story of the Corsair's impact reveals something profound about technological competition. Japan hadn't lost the naval air war because of material shortages alone. They had lost because American engineers had reimagined fighter design, while Japanese aviation remained committed to pre-war philosophies until it was too late. When American carriers launched their first raids against the Japanese home islands in February 1945, Miyazaki watched from an observation post near Yokosuka Naval Base. Corsairs swept in at wave-top height, their distinctive whistling sound announcing their arrival seconds before their guns opened fire on ground targets. "This is not just better equipment," he told a young assistant engineer beside him. "This is a different approach to warfare itself. Their entire industrial system is integrated in ways ours is not." The observation cut to the heart of why American aviation had achieved such dominance. The Corsair wasn't merely an excellent aircraft. It was the product of an industrial, educational, and philosophical system that approached problems differently. The Americans had built not just better aircraft, but better ways of building aircraft. The Corsair's development had involved every aspect of the American system working in concert. Universities provided theoretical research in aerodynamics and materials science. Private industry applied that research to practical problems. Government coordinated resources and requirements. Each component functioned as part of a larger whole. This systems-based approach extended to tactics and training. As American pilots encountered the Corsair's handling characteristics, they developed tactics that maximized its strengths and minimized its weaknesses. These tactics were systematically documented, analyzed, and distributed throughout naval aviation. Pilot training evolved to emphasize these new approaches. When Lieutenant Alexander Todd joined VF-18 Squadron in June 1944, he entered a training pipeline specifically designed around the Corsair's capabilities. He wasn't taught to dogfight in the traditional sense. He was taught to use speed and power to control engagements, to never turn with Japanese fighters, to make slashing attacks from altitude. "We don't fight on their terms," his instructor had explained during training. "We fight on ours. If you find yourself in a turning battle with a zero, you've already made a mistake." This philosophy, refusing to engage on the enemy's terms, represented American pragmatism applied to air combat. It recognized that different aircraft had different strengths, and victory came from exploiting your advantages while avoiding situations that emphasized your disadvantages. Japanese naval aviation, with its emphasis on individual pilot skill and traditional dogfighting excellence, struggled to adapt to this new paradigm. By the time Japanese training programs began emphasizing energy tactics rather than turning ability, the pool of experienced instructors had been decimated in combat. The Corsair's success revealed another often overlooked factor in wartime technological competition: feedback loops. American aircraft designers maintained constant communication with frontline units. Combat reports flowed back to engineering teams, who incorporated lessons into production blocks, sometimes within weeks. When early Corsairs showed a tendency to bounce on carrier landings due to their stiff landing gear, engineers modified the oleo struts within 2 production blocks. When pilots reported visibility issues during landing approaches, designers modified the cockpit canopy. Each improvement came rapidly because the system was designed for adaptation. Japanese naval aviation lacked this tight feedback loop. Combat reports took months to reach design teams. Manufacturing changes required extensive retooling in production systems not designed for rapid modification. By the time improvements reached frontline units, they were often addressing problems that had evolved or been superseded by new challenges. This difference in adaptation speed became increasingly apparent as the war progressed. By 1945, the Corsair had evolved through multiple production variants, each incorporating combat lessons and technical improvements. The basic airframe remained recognizable, but internal systems, armament, and performance had all improved substantially. In contrast, Japanese fighters like the Zero underwent fewer significant revisions. Improvements came slowly and incrementally. When more advanced designs finally emerged, production difficulties prevented them from reaching frontline units in meaningful numbers. The lesson was clear to engineers like Miyazaki, who studied both systems. Victory in modern warfare required not just good initial designs, but systematic approaches to improvement, production, and tactical employment. The Corsair exemplified this approach. It wasn't perfect when first deployed, but it improved rapidly through systematic feedback and adaptation. As Japan prepared for the expected American invasion in 1945, Miyazaki found himself tasked with developing countermeasures against Corsair ground attack capabilities. The assignment was nearly impossible. With limited fuel, materials, and trained pilots, Japan could not hope to challenge American air superiority. Yet, in this desperate situation, Miyazaki found unexpected inspiration. Studying the Corsair had transformed his understanding of aircraft design. He recognized that Japanese aviation had been constrained not just by material shortages, but by philosophical limitations, an unwillingness to challenge fundamental assumptions about what made effective fighter aircraft. In his final wartime memo to the Naval Air Technical Arsenal, Miyazaki wrote words that would prove prophetic for Japan's post-war aviation industry. "When this conflict ends, we must rebuild our approach to aircraft design from first principles. The lessons of the Corsair are not about specific components, but about integrated systems, thinking. This is the future of aviation." After Japan's surrender in August 1945, Miyazaki's expertise made him valuable to occupation authorities documenting Japanese aviation technology. American engineers were surprised by his comprehensive understanding of Corsair systems, in some cases more detailed than their own knowledge. Captain William Morrison, of the U.S. Naval Technical Mission to Japan, interviewed Miyazaki extensively in October 1945. "You seem to understand our aircraft better than some of our own engineers," Morrison commented after one particularly insightful explanation of the Corsair's wing-folding mechanism. "When your life depends on understanding something, you study it very carefully," Miyazaki replied. "The Corsair taught us that we had been asking the wrong questions about fighter design. We optimized for the wrong characteristics." This insight, that asking the right questions matters more than finding perfect answers to the wrong questions, became central to Japan's post-war industrial philosophy. Engineers like Miyazaki, who had studied American production systems, formed the foundation of Japan's economic recovery. When Miyazaki joined Mitsubishi Heavy Industries in 1952 as the company resumed aircraft production under American supervision, he brought with him the lessons learned from studying the Corsair. The systems integration approach became a cornerstone of Japanese manufacturing philosophy. The story of Miyazaki's analysis of the Corsair is ultimately a story about intellectual adaptation, about recognizing when fundamental assumptions need to be questioned. It demonstrates conclusively that how engineers think, how they approach problems, how they structure development processes, these intangible factors can be as important as raw materials and production capacity. The Corsair of 1943 had fewer technological advancements than many realize. It used aluminum alloys similar to those available to Japanese manufacturers. Its engine, while more powerful, used engineering principles that Japanese engineers understood perfectly well. The radios, hydraulics, and control systems employed technologies that were not mysterious or magical. What made the Corsair exceptional was how these elements were integrated into a cohesive system, how production was organized to create thousands of nearly identical aircraft, how tactics were developed to exploit its performance advantages. This systematic approach created capabilities that seemed impossible to opponents still thinking about components rather than systems. The lessons remained profoundly relevant for understanding technological development beyond simple metrics of performance specifications. Capability is not purely a function of materials or individual components. It is fundamentally a function of how systems are designed, how production is organized, how feedback drives improvement, how tactics exploit technical advantages. The American aviation industry of 1943 had turned these intangible factors into a systematic approach that changed warfare permanently. That system eventually produced not just victory, but a transformation in how complex machines were designed, built, and employed. When aerospace engineers today analyze the Corsair's impact, the conclusion remains clear across decades of scholarship. America built a fighter that emphasized power and speed over traditional metrics, that gave pilots the ability to dictate engagement parameters that could be mass-produced without sacrificing quality. This created a tempo of operations and level of tactical flexibility that opponents initially could not match. The advantage was temporary, lasting only until opponents learned similar methods and applied them with their own innovations. But for a critical period in history, it created air superiority that shaped the Pacific War and demonstrated principles that would reshape all modern aviation. The American aviation industry of 1943, it was not invincible, as wartime propaganda sometimes claimed. It was simply operating on principles opponents had not yet mastered, applied by engineers trained systematically over 2 decades. Once those principles became common knowledge, once Japanese aviation adopted similar methods in the post-war era, the advantage disappeared completely. But the achievement remains historically remarkable and worthy of serious study. Through systems integration, industrial organization, and tactical development that matched technology to fighting methods, America created aircraft that could defeat opponents through speed, power, and firepower rather than traditional dogfighting ability. That achievement, studied and learned from by all modern aerospace industries, stands as testimony to the enduring power of how engineers think, how they organize production, and how they match technology to tactical requirements. The methods pioneered in developing the Corsair, stripped of their wartime context, became foundational elements of modern aviation development and remain relevant to understanding technological effectiveness in any era. The transformation of engineers like Takashi Miyazaki, who witnessed American effectiveness firsthand and later helped rebuild Japanese industry based on those lessons, represents the broader recognition that what America achieved technologically was worth studying and learning from, even by those who had fought against it. Miyazaki himself would go on to lead aerospace projects that helped establish Japan's post-war aviation industry, applying lessons learned from studying the Corsair. His journey from examining a crashed American fighter at Kagoshima in 1943 to helping lead Japan's aerospace renaissance reflects the broader learning process that transformed defeated adversaries into economic powerhouses. The story of the Corsair's impact is not a story of American superiority or inherent advantage. It is a story of what systematic preparation, integrated thinking, and industrial organization can achieve when applied consistently. It is a testament to the power of questioning fundamental assumptions, the importance of feedback loops, and the decisive advantage that comes from designing systems rather than components. These lessons transcend the specific historical context and remain relevant for any organization facing technological competition in complex, rapidly changing environments. The Corsair's early success demonstrated that victory comes not from resources alone, but from how those resources are organized, developed, and employed. The subsequent Japanese adaptation demonstrated that even superior methods can be learned and adopted when organizations commit to fundamental change. The complete story provides insights into technological development, organizational learning, and the relationship between technical capabilities and tactical employment that engineers continue to study today. The methods that made the Corsair so effective live on in modern aviation, a lasting legacy of systems thinking, meeting the requirements of modern warfare. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.